So in order to deal with those problems, we're going to introduce an extension to Markov decision processes called TTD MDPs, as opposed to plain old MDPs.
TTD MDPs.
TTD MDPs, because it rolls off the tongue.
What does it mean?
Well, it means targeted trajectory distribution.
Oh.
Obviously. And that actually, you can see that when you think about how we go from an MDP to a TTD MDP. So what we try to do here is we want to make explicit those things that we said before. So instead of having states, we now have trajectories. And that's just all partial plot sequences that we can have, that we can reach, that we can get to. So it's the sequence so far. It's the story so far. I try to go back and forth between trajectories and sequences as opposed to stories because this is actually more general than the story example that we're using. Actions are exactly the same as they were before. We have a model, but now because we have trajectories instead of states, we have a model that says, well, if I'm in a trajectory and I take a particular action, what's the next trajectory that I will see? But it's still basically the same thing, except it elevates this notion of trajectories to sort of to a first-class citizen, and that we're reasoning over trajectories now. And now instead of having a simple reward, we have a target distribution. Now here I've made a sort of capital T instead of a lowercase t, and that's because the lowercase t here was sort of standing for trajectories. The capital T stands for final trajectories.
Uh-oh.
That is, ends of stories. So you don't have a distribution, or I guess you could say have a probability of 0 for all partial distribution, but all what we really care about is stories that we care about. So things that have higher probability are stories that you might consider good, and things that have lower probability, stories that you might consider bad or less desirable. Does that make sense?
I guess so, but why not just pick the one that we want and just and call that, I guess the distribution where the right story has probability of 1 and everything else is 0 seems to make sense.
Right, so that's a sort of strict generalization of what we were talking about. This is a strict generalization of what we were talking about before. So this allows us to say some things are better than others, and it turns out by relaxing this hard constraint that I'm trying to maximize reward, but instead I'm trying to match a distribution. It allows more replayability, it allows players to do a few more things, because now our goal is not to find a policy that maps states to actions in order to maximize long-term reward. It's to find a probabilistic policy. That is, a probability distribution over actions. Okay? And what is the optimal policy? It's the one that, if I use this probability distribution, would lead to be matching the target distribution.
I see.
Right?
Now, and so that I'm still on board here, the actions here are the things that the story can do.
Right, the story or the story manager or the system can do.
And the uncertainty for that thing, the uncertainty is, well, what is the player actually going to do? We don't know.
Right.
Okay, so it's not the player's actions, it's the story's actions.
Right, right, exactly. It's story actions or system actions or manager actions. There are lots of ways to sort of think about
things like we're going to make a wolf appear right about now.
Woo! Yes, exactly. That was me doing a wolf.
Oh, shoot, I was really scared.
Or I'm going to make a key appear. Or I'm going to unlock a door. I'm going to lock a door because I don't want you to go in this room.
Got it.
Right. So these are the kind of actions that you might be able to take in the system. The model says, well, if I'm in some trajectory and I take one of these story actions, what plot point will I end up in next? What trajectory will I see next? That depends upon the player. And so all of your uncertainty here sort of probably comes from the player. That's where all your entropy comes from.
Okay.
And I'm trying to get some stories. And some stories I want to happen more often than others, but this allows the player agency by doing this sort of probability distribution. Now, there's a lot of math that I could do here, but at the end of the day, what you might think is that, well, now that I no longer have this sort of simple constraint of maximizing my long-term expected reward, but I have probabilities and randomness and probabilistic policies, this is going to be harder, much harder to deal with.
Oh.
But it turns out it's not. As is often the case in machine learning and AI, if you relax a hard constraint and make it a soft constraint, you make it something that's more about probabilities and probabilistic sort of search, you actually get more power out of it and you're able to solve hard problems. So without going into the details, I can point you to a paper that you can, or actually a series of papers that you can read here. It turns out that by going from a hard constraint to probability distributions, you can actually solve a TTD MDP in linear time.
Linear in what?
Linear in the length of a story.
That seems unlikely.
Well, I could prove it to you, but instead what I'm doing is have you read the paper.